Do I really want to be recorded, or do you just want the deep DJ voice? You want the deep DJ voice? Thank you for coming to IWACO again after lunch. We're all fall asleep, but luckily we have Yichen here to talk about a paper on the mechanized theory of box calculus. You all have heard an awful lot about the box calculus this morning, I know, with Martin's talk and everything. So. Yeah, so anyway, good to kick off again. And as I've already said, we'll have 3 talks in this session, then a break. And just before we go to the break, I will see what people would like to do this afternoon. Effectively, you can start thinking about this. We do have the room for a 4th session if we want it. Previous IWACOs have had some level of discussion about what people are doing, perhaps if people hadn't had a chance to present, or if questions have emerged that it might be useful to talk about. Or alternatively, we can go to sleep or go to the pub. Anyway, Yichen.
Okay, cool, thank you. So today I'm Yichen Xu, and I'm going to talk about the mechanization of the capture calculus you just saw in the morning, and we call it box calculus. There are some historical reasons, and we'll explain it. So I'm Yichen Xu, and this mechanization is done by the first order Joseph, and I'm going to present on behalf of him because he cannot make it today. Okay, wait. Okay. I think it died. Okay. 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 Is it okay? I cannot see my cursor anymore.
We can disconnect the cable and then try it.
Like that. Okay, and
Still stuck.
it's still not working, I think. Okay. It's not responding. Yeah. Okay.
I don't know how it works somehow.
Not sure what's going on here. I cannot see the cursor. Okay, it's back.
Okay, and where was it? Do you know?
It's
on the flash drive?
But I think I can copy it out so that it can be more seamless.
Just turn on.
Okay. Thank you.
Yes, Finder. Thank you.
Okay, and there's a USB drive, and maybe let's copy it.
Which one is it? This one?
The first one, the mechanized theory. Okay. Okay, that worked.
Then we need to move it.
Over there.
But
It's
yes.
working, it's working.
This way?
Yes, okay.
And then
there's view, and I think this command might work. Does that work? Okay, no, okay.
yes, it did.
Okay, nice, thank you so much. Okay. Sorry, we wasted 5 minutes, but I can speak faster. Yep, so this is basically a mechanization of capture calculus. And what is it? So we've talked about it in the morning, but basically it is experimental new statistical analysis implemented in the Scala compiler that supports lots of things like checked exceptions and memory region management, and also like things like algebraic effects. So, and capture calculus, it is the theoretical foundation of capture checking. And so it basically idea is that it will check abilities in types, and it is capable of ensuring the scope of scoped capabilities. No. Okay, it's not dying. Okay, so to investigate capture checking, we actually have quite some attempts, and the box calculus or capture calculus is now the final outcome. And previously we have system CF sub, and we already have a mechanized proof of system CF sub. And there is a main difference between CC and CF sub, which is CC is now in monadic normal form. And so previously we have migrated the proof of CF sub to use monadic normal form too. And this project yet further migrated such proof to mechanized CC. Okay, so this is a nice diagram of the development of these mechanizations. And okay, we'll first talk about what is those capture calculi. And the first version, CF sub, maybe not the first, but one version which is on which our mechanization is based on is CF sub, and it looks very much like CC. And for the main difference from it to between it and the system F sub is that now types, they have an additional qualifier called capture sets, and the capture set, it can either be the root capability or a set of captured variables. And for other constructs, it looks very much the same as in system F sub. And there is one problem of it. So in the end, we find out that to do its soundness, we have this polarized, well-formed judgment. And this is really complicated. And another challenge of system CF sub is that it has a limited expressiveness power in terms of generics. For instance, let's see this example. Sorry. The cell type is just a church encoding of a container of one single element. And if we want to write a function which maps the cell, we apply a function on the element inside the cell, we can possibly write it this way. And but it is really straightforward. But the problem is that we have to decide the capture set of the result type. And what is it? Hopefully, it should be it should be the capture set of B. But we don't know what it really is. So in the formalism, the best we can write is just a star, which is the top in the capture set hierarchy. So that is really imprecise. But if we can force the generics to force the type variables to be pure, and without any capture set, for instance, here we can assume that B yet is a pure thing, then actually we can make it more expressive. And to do that, we have a new device called boxes. And to box a type, we can encapsulate what is captured in this capturing type into a pure type. And later on, we unbox it. And for those generic functions, we just assume that the type variables, they are pure. And that will give us a precise signature of such functions. And we can use the box mechanisms to properly reason about what is actually captured under the hood. And yes, that's why we introduced system F sub, system CC. And so first of all, it is in monadic normal form. And secondly, we add the box and unbox mechanisms into CC. And so the main difference we enforced is that for type variables, they must have a pure upper bound and a pure instantiation. So we don't have to think about, well, which capture set you put on these type variables. It's just pure, and all the captures are hidden in the boxes. Okay, so previously we have the distinction between pre-types and types. So for pre-types, it's just the types without a capture set. And for types in CF sub, it is a type qualified with a capture set. But in CC, we don't really still maintain this distinction. It's still stratified, but we can implicitly make a shape type or a type without a capture set to a capturing type by putting an empty capture set on it. So And also, we have this new formulation, and the key difference is that the type variable previously is considered as a capturing type. It can have a capture set under the hood, but here it is considered as a pure type. Okay, I think there's a mistake. Yeah, no mistake. So here it is considered as a pure type without any capturing. And the full expressiveness is, of course, recovered by the boxed and unboxed mechanisms, because we can now make a capturing type into a pure type and then later reveal the hidden capture sets inside the box. And now, with this formalization, we have much simpler well-formed judgment. So it's just standard. The only thing is that the capture set, it can only mention defined program variables in the context, and other than that, that is the same as the well-formed judgment in system fsub. And the main typing rule with the box mechanism is just these two ones, and one is the introduction rule for boxes, and another is the elimination rule for boxes. So, and note that we cannot box or unbox when the captured variables, which is C here, isn't in scope. So this is how we ensure scopeness in capture calculus. So then we did the mechanization, and we made one simplification. So previously, because we have the distinction between pretypes and types, and that basically shape type, the ordinary types and the ordinary types plus a capture set, we have this mutually inductive construct in the old Coq proof for CF sub. But Coq isn't very good at dealing with those mutual inductions, and it might take a long time to find the decreasing order of these inductions and make the proof check really slow. And now what we did is that we can merge these two types into one. So we put all the type definitions into one inductive type, and we have one additional judgment which checks whether a type is pure or not. And in most of times, we can just state one theorem on this data type instead of state two mutually inductive ones. And when we really need to have a mutually inductive theorem, we will use the pure judgment to differentiate between pure types and capturing types. Okay, so, and also, other than this simplification, because now our well-formed judgment is much simpler, it is a huge simplification in the mechanization too. And there are some possible future works that could make the proof check faster. So basically, our proof is in monadic normal form. Is in locally nameless with a cofinite quantification. So that's kind of a classical setting. And here, in some cases, we will use that pick fresh tactic to find a fresh variable that is not mentioned in the current context. And for that one, the tactic have to gather all the exclusion list, which is names already present in the context, and pick a fresh one. And we have those tactics which will work on this exclusion list to reason about it is distinct from anything else. But here, actually, the list by default will include all the atoms or names in the system, which includes both variables and type variables. So we think that if we can differentiate between variables and the type variables by just parameterizing its type with a tag, then we can get a smaller L in most cases. And because such cases are really common in the locally nameless proof, we think this can further speed up proof check. And so I can conclude my talk. And so CC is the box calculus is basically a huge simplification from CF sub. And with the introduction of the box constructs, it have and monadic normal forms. It have simpler, well-formed judgment, and it can have better expressiveness in terms of generics. And also, previously, the Coq proof of CF-sub is 12,000 lines of code, but after we migrating it to CC, it is only 7,000 lines of code, and it's almost halved. So this is a good proof that the new system is kind of better than the old one. And finally, the soundness proof is online available on this link, and there is a technical report of our mechanization as this URL too. It's okay, and that's all. Thank you.
It's a pretty quick talk. Does anyone have any questions?
Thank you. It's a huge work. Congratulations. How much can I reuse?
Well, if that depends on what your system look like. If that's somehow similar to capture calculus, like you want to track captured variables or track a set of things in your types, then I think a lot of infrastructures for those related to finite sets and how we deal with these types can be reused. But if your system is quite different, then I don't think it is easily reusable. And yeah, that's it.
Just a clarification. So, for instance, you have a small algebra for for reasoning on the capture, right?
No, we didn't abstract it as an algebra. Yeah.
Because I was going to propose, if that's something separate, can we just put there a different algebra?
That's a good idea. Yep.
Any more questions?
Also, it seems that one of the advantages of this is that you wrap up the generics, and then you can wrap up any capture thing in a generic, and then effectively when it's in a box, you can be passed around anywhere. Have you thought about possibilities of constraining that?
Constrain that?
Yeah, I mean, maybe you don't want to be able. I mean, for example, if you wanted to model, I shouldn't say this, a Rust-style ownership with generics, there are always constraints about where you need to maintain references or otherwise to objects. And it seems to me if you put an object into a generic container and now you can move that anywhere, you wouldn't be able to maintain the necessary invariance over the Rust heap. This isn't a criticism of your work, but it's not clear how it would be applicable in that case, is what I'm thinking.
Okay. I think currently with the box mechanisms, we do enforce some sort of constraints, which is the scope of the capabilities. So if you box something that captures, say, can throw, so the capability to handle exception, and that box thing escape the scope of the exception handler, then you cannot unbox it and use the value again.
Right,
so,
but it still exists.
Yes, still exists. But you cannot use it, so...
But it still needs to exist. And if I'm just really trying to see the limits of the way the system works. It's not a criticism of your work. For something like can throw, that's probably absolutely fine.
Yep.
But if you wanted to use this to do memory allocation, for example, if something escapes in just the same way, it's now escaped.
But if it doesn't, if you cannot use it, then it's fine. It's like having a pointer but not having the right to the reference. You can have a pointer; it's a useless value.
Well, yeah, you can. Indeed, you can, unless it gets garbage collected or whatever.
Yeah, sure, but we don't know what using the value means. Like if you're not allowed to use the value in any way, then you just have a useless value floating around your program, and you cannot do anything useful with it.
Sure, I know that, until you can unpack it.
but you can't unpack it, as you said. So you would capture your pointer that has a valid that points to valid memory. Then it escapes, so it no longer points to valid memory, but you can't use it. So you can't dereference it. So it's fine. Like nothing bad happens. You just have a big pattern.
Okay. All right. Well, thank you anyway.
Hello. Yes. So maybe a more cock technical question, but so if I understand correctly, this other system CF sub has this mutually recursive, mutually inductive definition, and cock doesn't handle that very nicely. And in the CC sub box, you do this trick where you do a single thing and then you have an inductive thing that says it's well formed if blah 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 blah, and then that simplifies everything. How much of these 7,000 lines is that simplification? Could you play the same trick on CF sub and reduce the size of that as well and the complexity of that as well, or
I think that's a good point. I'm not sure, but I won't say that this trick is reducing the lines of code that much, because the cases, they are still there, but they are just merged into one theorem. So,
right.
Yeah.
Okay.
I guess that's all. Let's thank the speaker again.